Hey guys, welcome back to this new video. Today we are going to take a look at GAN model. So what exactly is GAN? What is the internal working of a GAN model? What is the architecture of building a GAN model? And I'm going to show you a really good resource of learning about how to build a GAN model and what are the different types of GAN models that we have available right now. And also we're going to take a just quick look at the original paper of GAN model. Okay, so without wasting any more time, let's get started. So first of all, what exactly is GAN? GAN stands for Generative Adversarial Network, and if you want to learn about GAN models and different kinds of GAN models, I highly recommend you to go to the TensorFlow tutorials page, and under the generative section you have DC GAN, which is Deep Convolution GAN. You can go through this entire page to briefly understand what is GAN, how exactly is it generated, the internal working of it and everything. And here you can find different types of GAN models that we have right now. So stable diffusion, neural style transfer, these are all different variations of GAN models. One of the most basic GAN model is just the convolution GAN, and a little advanced level is going to be conditional GAN. We are going to talk about conditional GANs in the next video, but for now let's just understand what is basically a GAN model. So what is GAN? GAN is a generative model which is going to generate something, generate an image perhaps, or generate an audio clip. Could be anything, okay, but in this case we are going to look at how we are going to use a GAN model to generate an image. Okay, so what are GANs? GANs are generative adversarial networks, and these are the most interesting ideas today, because the idea of having an image that's very photorealistic and yet is not real is completely brand new to us. It's very interesting science fiction kind of idea, and let's understand how GANs are able to build those kind of things. So if you have seen the recent publications or even the recent trendings on social media, we can see that this image has been generated by AI completely from scratch, we have apps that take images of existing people, celebrities and all, and then convert them into something more of a oil painting or something more like how to say this, fantasy theme or cyberpunk themes. So all of these are built with the help of GANs. Okay, so all these models are just complicated versions of GANs, but the underlying code, underlying architecture, underlying algorithm that we are using remains the same. Okay, so GAN is basically a generative model. Okay, we are going to use GANs to generate images. Let's see how GAN works internally. So there are two models basically. One is the generator model, the other is going to be a discriminator model. My generator model is the actual model that's going to generate these photorealistic images, and my discriminator, it's a binary classifier. My discriminator is going to tell whether whatever my generator has generated is real or not, realistic or not. Okay, so there are two parts of my GAN model. One is the generator, the other is the discriminator. Generator is the artist. This is directly taken from TensorFlow. So as per TensorFlow, generator is the artist and the discriminator is the art critic. Okay, so in Keras, when we build the GAN, we're going to use two different models. The generator model is going to be a completely different model. It's going to be a sequential model with different layers, and my discriminator is going to be a different model, sequential model again, but the layers are going to be completely different, and the working of them is going to be very much different. The losses that we're using and everything else is going to be completely different. So generator and discriminator are two separate models. We're going to combine them to build GAN model. Okay, let's see how that works. One thing that we need to keep in mind is the data set. So for example, when I have the NVIDIA style GAN dataset, it's a huge dataset of faces. human faces, different races, different ethnicities, different ages, different variations, and different hairstyles, different skin colors, different genders. So there are going to be a lot of different combinations and different classes, but they all fall under one category, that is faces. Okay. By the way, all of this entire style GAN dataset has been generated using GANs. Okay. So if I take something like the style GAN dataset, I'm going to have only one class, only one thing that my model can learn from this, which is how does a face look like. Okay. So after my training, when I run my GAN model, the output that I'm going to get is going to be a face. Okay, a brand new face, someone who doesn't exist, someone who doesn't exist in the real world at all. I'm going to generate such kind of a face. Okay, but that's going to be very less complicated model, because the training time is also going to be very less, because I have just one class. If I go to something like the Caltech 101 dataset, I have nearly 100 or thousands and thousands of classes. So sometimes my model might generate a stop sign, a laptop, a horse, a plane. So every time I run my model, I might get a different output. So for that to happen, of course, that's going to be a really interesting model, but to build that model, I'm going to require lots of training time, lots of computation power. So the less number of classes you have, the less training time you need. More number of classes equal to more training time. Okay. So this is the architecture of generator model. So I'm going to use Keras to build a sequential layer, a sequential model, where I've got my dense layers, batch normalization layers, leaky ReLUs, very basic stuff. Okay, I'm going to explain what exactly is going to happen within this, but this is the internal architecture of generator model. Let's take a look at the discriminator model. The discriminator model is going to be a binary classifier. It's going to classify whether 0 or 1, true or false. So we are going to use this discriminator model to classify whether whatever image the generator has created, we're going to classify whether it's realistic or not. Okay. So these are the two models that we have, and these are the underlying code, underlying architecture of them. You can find this entire architecture along with the entire GAN notebook to build a GAN model notebook in TensorFlow tutorials page. Link is going to be in the description. Please do check it out. Okay, so let's get started. Right now we have three things. We looked at the data set that we're going to use, and we have a generator, and we have a discriminator. So if I go to next step, the things that I've indicated with red bounding box and red arrow marks, those are the things that we already have. So in every epoch, okay, for every epoch, I'm going to do two things. One is I'm going to tell my discriminator, I'm going to supply a real image and a fake image. Okay, so the real image, I'm going to get this real image from my dataset. So for every epoch, I'm going to take one image from my dataset, supply that to my discriminator. Simultaneously, I'm going to generate a fake image. Okay, so my generator is going to create a fake image, and I'm going to send that to my discriminator as well. So how does my generator create this fake image in the first place? It's going to take a latent vector. A latent vector is basically a vector. Vector is basically an array of integers, okay, array of numbers. It could be integers, could be float, anything, and that's what we call a vector, an array of numbers. But when I say latent vector, a vector usually has a direction, but a latent vector is a vector in latent space. There is no particular meaning to that vector. Okay, it doesn't indicate anything, it doesn't inform anything, it's not data, it's just random bunch of noise. Okay, so it could be something like minus 0.000781, minus 3, minus 1, minus 1.999, 2999.613, something like that, just an array of random values. That's going to be a latent vector. So it's a vector in latent space. For that reason we call it as a latent vector. So I'm going to take a list of random numbers, supply that as the input for my generator, and my generator is going to convert that into an image, and that's going to be a fake image, of course, because it has been generated from just a vector. Okay, it has not been taken using a camera or anything. It has been generated from a latent space, so it's a fake image. If I look at the generator model again, the very first layer, I'm going to have an input shape of 100. Okay, so this 100 is basically the number of values that I have in my latent vector. So from that latent vector, I'll take those 100 values, reshape them, and from all of these dense layers and convolution 2D transpose, which is basically upsampling, and from these upsampling layers I'm going to do batch normalization, upsample again, apply leaky relu activation function and all these things, and from all of these hidden layers I'm going to create one output which is going to be in the shape of 28 by 28 by 1. If you want to generate an RGB image, this is going to be 28 by 28 by 3. Let me take my pointer. Okay, so right now it is 1, so if I want to generate an RGB image, this is going to be 3. Okay, for this whole notebook I'm going to be using the MNIST dataset, MNIST, MNIST number dataset, and if you're familiar with it, then you know that it's a black and white image, black and white data. It's a dataset of black and white images. So for that purpose I'm going to take only one channel, which is white. So for every epoch I'm going to supply one real image and one fake image to my discriminator, and also to inform my I'm going to inform my discriminator that, hey, this image is real and this is fake. Okay, I'm going to inform my discriminator about that. To do that, whenever I send in a real image, I'm also going to send an array of ones. Okay, an array of 1 indicating that this image is real. Okay, so if I imagine my X train and Y train, I'm going to send in my X train, and also my Y train is going to be just a series of 1. Similarly, whenever I send my fake image, I'm going to send one more array of zeros, indicating that everything that I'm sending right now along with this fake image, so everything that I'm sending right now in this fake image is completely fake. So array of zeros, array of ones, that's going to be my Y train. So what this does is, it's going to teach my discriminator to learn and identify how does a real image look like and how does a fake image look like. Okay, so this is going to happen for every epoch. So for every epoch I'm going to take one real image, generate one fake image, send them to my discriminator, and I'm going to tell it which is real and which is fake. In the next step, once my discriminator learns them, in my next step, my generator is going to tell my discriminator to stop learning. Okay, so right now I've already shown you a real image, a fake image, so my discriminator knows a thing or two, but my generator is totally a dumb generator. It's a dumb model. It doesn't understand anything. So it's going to tell my discriminator, hey, since you've already learned a thing or two, stop learning, and then I'm going to send you one image and you need to classify whether that's real or not. Okay, so my discriminator is going to stop its learning, and it's going to take an input image and classify whether that's real or fake, realistic or fake. Okay, but every time I'm not going to send a real image at all. Every time I'm going to send a fake image. So again, I'm going to take a latent vector, a brand new latent vector, send it to my generator, and my generator is going to take it, convert that into an image, and I'm going to send that to my discriminator. Since my discriminator has already learned a thing or two about how a real one looks like and how a fake image looks like, this is going to classify whether this input image is real or fake. Okay, So I'm going to get a y predict value. It's going to give me a prediction that this image is real, this image is fake, so on and so forth. But if you look at right now, we are at the very beginning of the training. Assume that we are at the beginning of the training, and during the starting stages of training, my latent vector is just random noise and my generator is very dumb. So the image that I've generated, so whatever fake image that I'm giving here, it's pretty much obvious that it's fake. This is kind of how my generator has created an image from that latent vector, and this is how a real image looks like. So if you look at them visually, you can easily identify that these are completely two different images. And since my discriminator has already learned how a real image looks like and how a fake image looks like, it's going to give very high loss function, very high loss value. So my generator has created this, but my discriminator is going to say, hey, whatever input you have given to me is absolutely fake. So that's going to be my y predict. And I know that ideally this fake image is supposed to be very realistic, ideally. Okay, so when my model training is completely done, my generator should be able to generate images that are extremely realistic. So that would mean my y actual is a series of ones. Previously what I've given here is I'm saying that all these are fake, and I'm doing that by sending series of zeros. But at this stage I want my generator to be very smart, and I want my generator to create very realistic looking outputs. For that reason, to calculate this high loss, I'm going to send my y actual as a series of ones. This might be a little confusing. Try to rewind back and listen to this again. That's very simple once you understand it. Okay, so now I have my y predict, y actual. Using both of these values, I can easily calculate my discriminator loss. Okay, so this discriminator loss is basically going to tell me how good my generator is. So yeah, discriminator loss is going to tell me how good or how bad my generator is. High loss indicates that my generator is very bad. As you can see here, I've got a really high loss because my generator is very bad. But if the situations were the other way around, if I have very low loss, that would indicate that my generator is extremely talented. It's very robust. Okay, that's the ideal situation. That's where we want to reach. So let's see what happens next. Right now I've calculated my discriminator loss. Then I'm going to take this discriminator loss and send this to my generator like so. This is called as back propagation. So whatever loss that I've got here, I'm going to send that to my generator as back propagation. So my generator is going to take this loss and learn and understand where exactly did it go wrong. In the next iteration, whenever it's creating this fake image, it's going to optimize itself, and since it has already learned from the previous epoch, it's going to modify the weights and create something a little more realistic. Not completely realistic, but a little more closer to the real images, a little more closer to the real images. And it's going to send that to my discriminator, and I'm going to calculate this loss function again, and this loss will be sent to my generator again. It's going to optimize furthermore. So in every epoch, my generator is going to learn little by little based on this discrimination loss. Okay, so as you can see, now my generator learns and adjusts its weights using this loss. And also parallelly, I'm going to tell my discriminator that, hey, you can resume your learning part again. So I'm going to send one more real image, one more fake image, and tell the discriminator which is real, which is fake, how a real one looks like, how a fake one looks like. Now it's going to learn a little bit more again, and then I'm going to tell it to stop learning, and then my generator will take a latent vector, convert that into an image, send it, and ask my discriminator to classify whether it's real or not. I'm going to get a prediction, my y actual and y prediction. I've got both of those values. Using a metric, I can calculate the discriminator loss. If this loss is high again, I'm going to use back propagation, send it back to generator, keep repeating this process. Ideally, at some point, my discriminator will not be able to identify or differentiate between real and fake image. So if my discriminator loss is extremely low, that basically says or indicates that my generator has become very robust to a point where it can generate extremely realistic looking images. Since I have all of these, if I go back to the original slides, since I have all of these dense layers and collision layers here, my generator is going to learn at every step. I'll go through the code later on, but you can see that there is no model.compile here. We're not compiling this because I'm going to ask my generator to learn only with the help of back propagation. Only with the help of this back propagation, this part. And for that reason I don't have model.compile there. But yeah, coming back to the point, after a certain number of epochs, after training for a while, my generator is going to become very knowledgeable to a point where all of its weights are adjusted such that the output image from this generator, whatever I'm getting here, the fake image, it should be extremely realistic, and my discriminator fails to classify that as fake. So it's going to say, oh okay, whatever I received is a real image. So in that case, both of these values will be extremely closer to each other, series of ones, series of ones. So my discriminator loss is going to be very low. So if the discriminator reaches the lowest point, if the loss has reached completely the lowest point, then I can go ahead and stop the training. So that basically indicates that my generator has learned enough to fool the discriminator perfectly. So fooling the discriminator is basically generating very realistic looking images, right? So my generator has completely evolved and adjusted all of the weights such that it's going to generate completely realistic looking images. At that point, I can go ahead and stop the training. If not, again, as I told you, everything goes back to the first step, new epoch, send a real image, a fake image, give it labels, stop the training, send a fake image, get the predictions, calculate discriminator loss, back propagation. This is going to happen, and if the loss is very low, I'm going to stop my training. This is the basic architecture of how a GAN works. So after a certain number of epochs, after certain training time, my generator is completely robust. So I'm going to stop my training and export this generator model and keep doing model.predict to get vectors converted, keep doing model.predict to get images that are created from scratch. As simple as that. So if you see here on the left, I have model training images. So during my training, let's say after first epoch, second epoch and third epoch, I'm exporting those images and putting them in the form of GIF or GIF. Okay, so if you see, we are beginning everything with a latent vector. So the entire square is filled up with random noise, and in the second epoch I'm getting somewhat of a definite shape. In the third vector I'm getting a little better shape, and in the fourth, fifth and sixth vector, the shape of that number, that symbol, is getting optimized slowly. Okay, so it's going to my generator is learning at every epoch to fool the discriminator. It's going to try very different permutations and combinations and different iterations of adjusting the weights such that my discriminator loss is reduced. So wherever the loss is reduced, it's going to favor more in that direction, and if it does something that's increasing the loss a little bit again, it's going to avoid doing that, come back to its original position and keep going in that particular direction. Stochastic gradient descent. But yeah, so this is how the generated images looks like during the training. Once the entire training is done, once the discrimination loss reaches the lowest point, I'm going to stop. The model training is going to stop, and when I export my model and do model.predict, these are the outputs that I get. These are very much realistic looking, and if you know how the MNIST dataset looks like, you will not be able to identify whether this is directly from the MNIST or from a GAN model. That's how realistic these look. Okay, so this is how we generate fake images. This is the paper that discusses about GANs. So this is the very first paper that was published on GANs in the year 2016, written by these three folks. It was proposed in 2016, but most of the applications, most of the well-known applications that we have right now, such as conditional GANs or style transfer, pix-to-pix GANs, have been developed on top of the basic generative adversarial networks. So convolution GANs are the very basic form of GANs, and there are other variations, as I've told you. The style transfer or the pix-to-pix or conditional GAN, all these have been developed based on this paper written by these three folks. And one more interesting thing is Soumit Chintala, the guy that you see here, he is actually one of the creator of PyTorch library. So he's one of the creator of PyTorch library, and he has worked with these two folks to create GAN model, the very first GAN model the world has ever seen. So yeah, I think that's pretty much it about this internal working of GAN. So today we looked at what exactly is a GAN, how does it work, what are the different kinds of models that we use for training the GAN, and what are the different types of data sets that we can use our GAN model on, and the architecture, the code of how GAN works, and also the very basic workflow of GAN model. And again, whatever you see on the right here are images completely generated with the help of a GAN and not directly from the MNIST dataset. So ideally, when you have an image dataset of just one class, you can take that. So for example, if I have let's take hyperquasit dataset. It's a dataset of GI track. Okay, so if I take that dataset and train a GAN model, I will be able to generate image from scratch which can be used for colonoscopy. Okay, or let's say if I have dataset of cats, for example, I can train my model on that dataset. I can generate a fake image of a cat. It's a completely fake image generated using AI. That cat doesn't exist, nobody has took that photo, but it looks extremely realistic. So these are some of the applications of GANs. Again, this conditional GAN is the most basic GAN, and there are many other variations of GAN that you can start looking at. I'm going to make a few more videos on them as well, but yeah, these are the very basic convolution generative adversarial networks. Thank you for watching. See you in the next video.